Hi, I'm Ed Rhodes. I'm a professor of geology here in Earth and Space Sciences, and we're here in my laboratory where we do luminescence measurements. There's a range of techniques that we do, something called TL or thermoluminescence, and something called optically stimulated luminescence and infrared stimulated luminescence. All of these techniques we're applying to Earth materials, usually quartz grains and feldspar grains that we separated from rocks or loose sediments, and the applications that we're looking at are focused at understanding Earth's surface processes. Some of these processes involve paleoclimate, some of them involve fault movement and tectonics, and some of them involve events such as ancient heating. So if you can hear the machine beside me whirring away, then it's currently making measurements. In a few minutes we'll see some data beginning to appear on the screen. We're actually measuring the infrared stimulated luminescence from some grains of feldspar separated from granitic rocks in the San Bernardino Mountains here in Southern California. We're trying to develop a new technique that will allow us to determine what the rate at which the mountain range is being pushed up by forces within the Earth and the surface is being eroded off. So the grains start off as being hot because they're within the Earth, and as they approach the surface they cool. And only when they start to cool beyond a certain limit, and that we don't know exactly what that limit is, but it's of the order of 50 degrees centigrade to 25 degrees centigrade, then when they cool beyond that limit, they start to be able to trap electrons that are created by interaction with environmental radiation within the rock. And that gives rise to a signal. Oh, we have a signal here just developing on the screen. And the magnitude of that signal depends on the length of time that the grain has been trapping electrons. So we're developing this to form what we call a thermochronometer. And the exciting thing about this is the temperatures we're talking about are very low, which means that we can look at processes happening very close to the Earth's surface. Perhaps to understand the physical technique, it would be best if I show you what we actually work with. So we have here some small aluminium discs, and with some silicone oil we've stuck on some grains of quartz. So quartz is a very common rock-forming mineral. It's the most common constituent of clean beach sand, for example. And these grains were prepared from a sediment, and we've stuck them onto these aluminium discs. The aluminium discs we place on a holder, such as this. So perhaps I'll just put one in position to illustrate the way that we would do that. So we take one of the samples, put it on the holder, and the holder goes inside this machine behind me. The whole thing there is controlled by this computer off to the side. And we can take this sample and then bombard it with light, and the light is in a series of light-emitting diodes mounted in this block on the right-hand side of the machinery. And we hold the sample at a slightly increased temperature, and that allows the electrons that became trapped over periods of hundreds of thousands of years within those quartz grains. Since the quartz grain was last heated or exposed to daylight, the shining on of light in the machinery allows electrons to become untrapped. As they recombine in the crystal, they give out ultraviolet radiation, and we pick that up in this photomultiplier tube. You can see we have a warning on the photomultiplier tube that we have a certain set of filters in, so we mustn't turn on our blue light-emitting diodes, otherwise we'll have such a large signal we'll destroy the equipment. So we're currently doing infrared stimulated luminescence. The light that we're shining on the sample is infrared light. It's stimulating electrons to become untrapped. They're actually grains of feldspar that are in the machine at the moment, and they're recombining within the grain itself to produce a blue and ultraviolet signal that we're collecting. We collect it in this very sensitive light detector, and this is passed through to the electronics, and that passes the signal through to the computer where it's stored. We make a number of measurements on the same sample, and that allows us to compare the magnitude of the natural signal that we observed. So the first signal we measured, what was produced by the sample interacting with environmental radiation whilst it was buried in the ground, we compare that with the radiation that we induce in the laboratory. So on this side of the machine, we're able to induce trapped electrons by exposing the sample to ionizing radiation. So the whole procedure in the machine is a little bit complicated, and that's all controlled by the computer, moves around, and it gives us a series of measurements out. We take those into a different laboratory and we analyze them on a computer. We combine the different signals from different portions of the sample that we measure, and we look at this different response for different measurements made at different times through that. The main thing we're trying to do is find out basically how much radiation damage, it's a very soft form of radiation damage, that just in the form of trapped electrons, how much of that occurred before we got hold of the sample by digging it out of the ground or pushing it into a steel tube in a pit, for example. One of the advantages of the equipment is that it can easily be miniaturized. All we need to generate a signal is a very, very small light-emitting diode or a very small laser. And the detection equipment is also very straightforward, a photomultiplier tube, or that can be miniaturized to a solid-state detector. And that has huge advantages by comparison to many chemical techniques that require much larger or heavier equipment, for example, heavy magnets and those kind of pieces of equipment. Some of my colleagues in Denmark and in Oklahoma are developing systems to be sent to Mars. People may know that Mars has sand dunes on its surface, and more recently people have discovered evidence of water flow across the surface of Mars. And this technique, optically stimulated luminescence, can be applied in order to assess whether those processes are taking place at a fast rate or a slow rate, and how active those processes are. So they may be taking place in between measurements that we can make, for example, by remote sensing, and we can get a better assessment of that by measuring it directly. So people are currently building systems not very different from this system here, but miniaturized, which will sit on one of the future Mars rovers, and a small sample from under the surface will be collected by a specially designed arm, taken into the machine, and that will be dated. But there's still a lot we don't understand about the technique. So it's not straightforward that we will automatically be putting this on every spacecraft that's going to land on the surface of a planetary body. I think that probably there will be a lot of interest after the results from this future Mars mission, assuming that it does manage to get the funding, I hope it does, that can actually demonstrate the usefulness of luminescence measurements. But I won't make the prediction that this will be absolutely common on all missions in the future. But, we're very excited by the potential of the results that our colleagues will get from that mission.